Hello friends, welcome to my second lecture on solution of first order non-linear equations. In this lecture we shall discuss equations of the form ZPQ equal to 0 which come under the category type 2, and then we will also discuss equations of the form F1xp equal to F2yq, which where the variables x and p and the variables y and q can be separated. So that those equations come under the category of type 3. So we begin with the equations of the form FZPQ equal to 0 which come under the category type 2. Such type of equations contain only the partial derivatives p and q and the dependent variable z. What we do is, let us assume a tentative solution of this partial differential equation Fz equal to phi x plus ay, where a is an arbitrary constant. What we do further is that let us assume x plus ay to be equal to capital X, so that z becomes a function of x only. Now we know that p is the partial derivative of z with respect to x. So this partial derivative of z with respect to x can be expressed as dz by dx into delta x by the chain rule, and we see that delta x by if you differentiate capital X with respect to small x, what you get is 1. So delta x by delta x is equal to 1, and therefore p is equal to dz by dx. Here q is similarly q is delta z over delta y. So delta z over delta y can be written as dz over dx into delta x over delta phi, and this is equal to a dz over dx, because delta x over delta y if you find, then delta x over delta y is equal to a. So this will be giving you a dz by dx. Now substituting these values, the given partial differential equation is then reduced to f z, p is dz by dx, as we have seen p is dz by dx, and q is a dz by dx. So f z dz by dx, a dz by dx equal to 0, which is an ordinary differential equation of the first order, whose solution will give us the required complete integral. And once we have the complete integral, as we have seen earlier, the general and singular integrals are then found in the usual manner. Let us take the nonlinear equation q square equal to z square p square into 1 minus p square. So this is the differential equation of type 2, because here you can see we have only the partial derivatives p and q and the dependent variable z. So let us see how we solve this equation. So q square is equal to z square into p square 1 minus p square. Let us assume that z equal to phi of x plus ay, which is equal to phi of x, where x is equal to x plus ay. Then, as we have seen in the article, delta z by delta x will be equal to dz by dx into dx by delta x, and delta x, when we differentiate x with respect to x, delta x by delta x is equal to 1, so we get dz by dx. Similarly, delta z by delta y is equal to dz by dx into delta x by delta y, and when we differentiate x with respect to y, what we get is a. So a dz by dx. So let us put these values in the given differential equation. So substituting in the given partial differential equation, we have q square. This is q. Q square means a square dz by dx whole square equal to z square. Z is z, so z square, and p square. P is dz by dx whole square, and then 1 minus dz by dx whole square. Okay, so we can see that hence dz by dx equal to 0. Okay, dz by dx equal to 0 satisfies this equation. Now dz by dx equal to 0 means p is equal to 0 and also q equal to 0, which implies that p is equal to 0, q equal to 0, which means that the partial derivatives of z with respect to x and y both are 0. So it will mean that z is an arbitrary constant, some constant c, where c is an arbitrary constant. Okay. Now it is, since it is a trivial, so it is a trivial solution. Let us assume dz by dx to be not equal to 0. Okay. So let us assume dz by dx not equal to 0, then we shall have a square by z square equal to 1 minus dz by dx whole square. So then dz by dx whole square will be equal to 1 minus a square by z square, or we can say dz by dx will be equal to z square minus a square divided by z plus minus. Dz by dx equal to plus minus under root z square minus a square divided by z. So or we can say plus minus z over under root z square minus a square is equal to dx. Now this is when we so integrating this equation, what we get is under root z square minus a square equal to x plus some constant b. Okay, and this is this gives you then x plus ay plus b. Now squaring both sides, on squaring we have z square minus a square equal to x plus ay plus b whole square, which is the required complete integral, because it contains two arbitrary constants. Now as we know, to find the general integral, we put by b equal to some arbitrary function, say psi of a, and then differentiate this equation with respect to a. Then we eliminate a from this equation and the equation that we get by differentiating this equation with respect to a after putting b equal to psi a. And in order to find the complete integral, we differentiate this equation with respect to a and put it equal to 0 and then differentiate this equation with respect to b, and then solve the three equations, this equation and the two equations that we obtained by differentiating with respect to a and b, and eliminate the arbitrary constants a and b to get the singular integral. So these general and singular integrals are obtained in the usual manner. Now let us go to next problem. So the next problem is q square by square equal to q square by square equal to z into z minus px. Now this equation is not in the standard form, that is type 2, because here the independent variables x and y are also occurring. So we will have to make a substitution in order to reduce this equation to the standard form. Suppose I define z equal to capital Z equal to ln z. Suppose we define, let us define capital X equal to small ln x, capital Y equal to ln y, then we shall have x into p equal to x delta z by delta x, and delta z by delta x can then be written as x times delta z by delta capital X into delta x by delta x. Now this, from here x equal to ln x, we have delta x by delta x as 1 by x. So we have x, this x cancel and we get it delta z by, here I have capital X. This, and similarly q into y is equal to q into delta z over delta y, which can be written as q times y times delta z over delta y, because q is delta z over delta y. So y times delta z over delta y, which can be written as y times delta z by delta x, and then delta x by delta y. Now when we differentiate, this can be written as delta z by delta y, and this is delta z y over delta y. Okay, let us write like this. So y times delta z over delta y into delta y over delta y is 1 over y. So this is delta z over delta y. Okay. So q by is equal to delta z over, thus the given equation reduces to delta z over delta y whole square equal to z into z minus x into p. X into p is delta z by delta x. Okay, so if we designate or if we denote delta z by delta x equal to capital P and delta z over delta y equal to capital Q, then we have q square plus equal to z into z minus capital P. So this equation contains only the partial derivatives P and Q and the dependent variable z. So it is of the, so this equation is of type 2. Okay. Now let us try to find the complete integral of this. So let us define z equal to some function of x plus ay, because here the independent variables now are capital X and capital Y. Okay, so let us call it as phi of u, where u is equal to capital X plus ay, and a is an arbitrary constant. Okay, so then delta z over delta x will be equal to, then p equal to delta z by delta x will be equal to dz by du into delta u by delta x, and delta u by delta x is equal to 1. So we have dz by du, and capital Q will be equal to delta z by delta y, which will be equal to dz by du into du by delta u by delta y. Delta u over delta y is equal to a, so we have a dz by du. Let us replace these values of p and q in the equation. Let us call it as 1. So substituting these values in equation 1, we will get a square dz by du whole square equal to z square minus z into p. So z into p is dz by du. So a square dz by du whole square equal to z square minus z into p. So we have this. Now r a square dz by du whole square plus z dz by du minus z square equal to 0. Now it is a quadratic equation in dz by du, so we can solve it. So then dz by du can be obtained from here, which will be minus z plus minus under root z square plus 4a square z square divided by 2a square. Okay, so this is equal to minus 1 plus minus under root 1 plus 4a square by 2a square into z. Now we can differentiate it easily, we can integrate it easily. So integrating so we can write it as 2a square upon minus 1 plus minus under root 1 plus 4a square into dz by z equal to du. Now integrating this, we will have minus 2a square upon minus 1 plus minus under root 1 plus 4a square ln z equal to say u plus, let us write ln b, and this will give you then z to the power minus 2a square divided by minus 1 plus minus under root 1 plus 4a square equal to b times e to the power u, or which is equal to b times e to the power u is equal to x plus ay which is equal to e to the power, now x is ln x and y is ln y. So this is ln x plus ln y to the power a, and which will give us ln x y to the power a. So we have b times x y to the power a, and thus z equal to z to the power minus 2a square divided by minus 1 plus minus under root 1 plus 4a square equal to b times x to the x into y to the power a is the complete integral. The general integral and the singular integrals are then found in the usual manner as we have discussed earlier. So this is the solution for the second example. Now let us go to equations of the type 3. So here we consider those types of equations, partial differential equations such that the variables x p and y q are separable, they can be separated. So in this type of partial differential equations, the variables x p, y and q can be separated. Let us say that means on one side we will have the expression involving x and p, on the right side we will have expression involving y and q, which we can write as f function of x and p and equal to some function of y and q. Now as a trial solution we will assume that f x p equal to g y q is equal to some arbitrary constant, let us say a, and then we will have f x p equal to a and g y q equal to a. So let us assume that these equations can be solved for the values of p and q, and when we solve f x p equal to a, we get say p equal to some function f1 of x and a and q as some function f2 of y and a. Then recalling that we have dz equal to p dx plus q dy because dz is the total differential. So p dx plus q dy, putting the values of p and q so obtained, we have dz equal to f1 xa dx plus f2 by a dy, and then we integrate on both sides to get z equal to integral of f1 xa dx plus integral of f2 by a dy plus some arbitrary constant v, and since this solution involves two arbitrary constants a and b corresponding to the two independent variables x and y, so it is the required complete integral. And once we have the complete integral, as we know, the general integral and the singular integrals can be found in the usual way. Okay, so let us study some examples on partial differential equation of type 3. So z square into p plus q equal to x square plus y square. Let us write it as r z square p minus x square equal to y square minus z square into q. Let us put it equal to some constant a, some arbitrary constant. Then z square p minus x square equal to a gives you p equal to a plus x square divided by z square, and similarly y square minus z square q equal to a gives you q equal to y square minus a divided by z square. Now let us recall that since dz equal to p dx plus q dy, we have a plus x square upon z square dz dx plus y square minus a divided by z square dz. Now let us multiply by z square. So r z square dz equal to a plus x square into dx plus y square minus a into dy, and it can be easily integrated. So, z cube by 3 equal to ax plus x cube by 3 y cube by 3 minus ay plus some constant, let us say b. Okay. So, this is the complete integral, and this is the solution of the given partial differential equation, which involves two arbitrary constant a and b. So, it is the complete integral, which is the complete integral. So, we can notice here one thing, that as such the given partial differential equation is such that the variables the variables x p and y q are separable. Okay. So, it is of the type 3, and here we notice that it can be then expressed as the values of p and q can be found as a plus x square by z square and q equal to y square minus a over z square. So, then we put them in the expression dz equal to p dx plus q dy and integrate in the usual way and obtain the complete integral. General and singular integrals can then be found as we have discussed already. Let us now take up another one, partial differential equation, to make it more clear. So, let us consider z square into p square plus q square, and then this is equal to x square plus y square. So, here I think we have to define, let capital Z be equal to because this can be, this is zp whole square and this is zq whole square. So, we have to define it as z square by 2. Then what will happen, delta z by delta x will be equal to delta z by delta z small z into delta z by delta x, and delta z by delta z will be from here, this will be equal to z. So, z into delta z by delta x, which is z into p, and delta z over delta y will be equal to delta z over delta z small z into delta small z by delta y. Delta z over delta z is z here, so z into delta z over delta small z. So, delta small z over delta y, which is equal to qz. Okay. So, zp is equal to delta z over delta x and qz is delta z over delta y. So, we have the given equation becomes delta z, this is capital Z by delta small x whole square plus delta z by delta y whole square equal to x square plus y square. Now, we can separate the variables, delta z by delta x whole square minus x square equal to y square minus delta z over delta y whole square. We can put it as some constant a and then solve for the values of delta z over delta z. So, delta z over delta x will be equal to a plus x square under root, and similarly delta z over delta y will be equal to y square minus a under root. Now, d capital Z equal to delta capital Z over delta x dx plus delta capital Z over delta y dy, and which is equal to under root a plus x square plus under root into dx plus under root y square minus a dy. Now, we can integrate this. So, integrating we get capital Z equal to integral under root a plus x square dx plus integral y square minus a dy plus some constant b, and then we put the capital value of the capital Z, which is z square by 2. So, z square by 2 equal to integral under root a plus x square dx plus integral under root y square minus a dy plus b. Now, you know the formula for the integral of under root a plus x square and the integral of under root y square minus a. So, apply those formulas to evaluate these integrals, and then we will have the complete integral, which involves two arbitrary constants, and the general and singular integrals are then found in the usual manner. So, which is the complete integral. With that, I would like to conclude my lecture. Thank you very much for your attention.